What occurred in the development of the two streams in their applications to BCI. They came together as a field, and the objective of this field was to do things with brain signals. Initially, the primary objective was for communication control. There were a number of factors besides these two streams, however, that produced the field of BCI. One was the increasing recognition by society of the abilities and the needs of people with disabilities. The realization that they can lead lives that are both enjoyable and also productive if their disabilities can be ameliorated, if the effects of their disabilities can be ameliorated by providing them, for example, with new means of communication and control. This has become an increasing focus in the last 20 or 30 years. Another major factor in the development of the field was the realization of the plasticity of the nervous system. And for those who have entered the field of this field or the field of neuroscience in general in the last 10 or 15 years, that it's hard to realize what the change has been over the past 30 or 40 years. 30 or 40 years ago, the central nervous system was viewed as a very hardwired system that could change very little after initial development. The changes were in very few places, in very limited ways, so that if you had damage from a stroke or a spinal cord injury or some other insult, there was really very little you could do. You could use what was left to work around it, but you really couldn't fix what was wrong. And over the last 20 or 30 years, we've come to realize that that's not true, that the nervous system has capabilities for plasticity that were previously unrealized, and our task at present is to understand these capabilities and to learn how to initiate and guide them to restore function. So that also made BCI research increasingly relevant, increasingly exciting and important, because BCIs provide new adaptive, new interactions with the nervous system, new ways to interact with the nervous system to initiate and guide plasticity. And that really gets to the third factor, which led to the development of brain-computer interface research and development, and also the fact that it developed now instead of 50 years ago or 50 years from now. And that's that it is very much dependent on technology, that it requires the establishment of high-speed, complex interactions with the nervous system. That requires technology. It requires software and it requires hardware. And up till the last several decades, that software and hardware either didn't exist or it was extremely cumbersome and expensive. Again, that has completely changed in the last several decades, so that it's now relatively easy to establish interactions from the hardware and software point of view, and therefore to access the nervous system's capability to use brain signals to communicate. So if we look at this, this is a BCI taking signals from the brain, processing them, and using them for a variety, basically 5 different kinds of applications. These are the 2 applications that had where the initial focus was, to restore communication and control to people who were paralyzed. And this is still a big area, and you'll hear tomorrow about current developments, the current state of that, from Nick Ramsey and from Lee Miller. But the other possible applications have now become very prominent, particularly the capacity to improve function, the idea that you could establish adaptive interactions with the nervous system that would initiate and guide plasticity to improve rehabilitation. This is a very exciting area, and this will be discussed tomorrow by Donatella Macchia and in our symposium tomorrow morning. Another 2 areas are the ability to enhance, the capacity to enhance central nervous system function or to supplement central nervous system function. These are applications that go beyond biomedical applications, applications designed to improve or restore function, and these will be addressed tomorrow by Jose Millan. Also, in general, there are these 5 different kinds of applications, but there's another area that was theoretically possible 10 or 20 years ago, is now actually becoming very active, and that's the use of BCI technology to explore central nervous system function, to establish interactions that allow us to explore the principles of how the central nervous system operates, the use of brain-computer interface technology for basic science applications. And tomorrow, Aaron Batista will talk about the current state of that new area. So all these areas are active at this point. They're very exciting. They're part of BCI research. There are a number of factors that really apply to all of them that are very important to consider at this point. I'm simply going to address one of them, which I think is particularly important for this meeting. And this is the fact that brain-computer interface research is inherently and necessarily and very fundamentally multidisciplinary research. So it starts obviously in neuroscience, in the understanding of the brain, and presumably the goal is the establishment of a useful brain-computer interface for some purpose, whether it's basic science or rehabilitation or communication and control. However, there are many disciplines that are essential for this besides neuroscience. Computer science is extremely important, biomedical engineering is important, materials engineering is important, signal analysis plays a crucial role, the behavioral sciences are very important, clinical sciences, as you move to translate what's done in the lab into actual use in the field, is very important. The regulatory requirements, such as FDA requirements, reimbursement, those issues become very important, particularly when you're developing clinical applications. Biomedical ethics becomes important. Clinical practice, what's actually going to be used out there? Will it be used? Will it be used in a way that the practitioners will want to use it and will be able to support it? And finally, dissemination. All these various areas and all these various disciplines become critical. And the only way that the BCI is finally arrived at is if all these areas are satisfied. So people, clearly each of us I don't believe any of us would really consider him or herself an expert in all of these areas. But we need to be aware of what's going on in the other areas and what aspects of them are particularly important for our goals in regard to developing a brain-computer interface. For example, if we're involved in signal analysis and we're looking to establish a communication or control BCI, we need to look at considering signal analysis that will be useful from day to day. It won't simply be able to be very effective in data obtained from over a period of a few hours, but the same algorithm can be easily translated to function the next day and the next week and the next month without elaborate recalculation. It's important that when we're looking at communication and control applications that we consider the population that we're setting out to serve. What are their disabilities? What do they need? How large is that population? Because if it isn't very large, it's going to be very difficult to get any company to actually manufacture and disseminate a BCI. It's important to consider what the competition is, what other kinds of communication and control devices are available for people in this situation. Are eye movement systems more capable than BCIs? Are EMG switches more capable? What exactly can the BCI offer that makes it worthwhile? At the same time, as we go forward in developing these systems, unusual things occur and unexpected things occur. And there are situations that develop in which really a very simple BCI with very limited capability may actually be able to perform a function that a overall much more capable eye movement system can't perform. These are things you only find out when you actually try to take things out of the laboratory and use them in people to do initial clinical translational research and determine what's effective. When you consider invasive BCIs, you're concerned about the ethics of putting in invasive devices. In what situations is it appropriate to do that? Is it worthwhile trying to do that? Is the BCI superior to what can be obtained in other ways, other BCI ways or other non-BCI devices? All these issues become very important, and the people in each one of these areas have very important roles to play. So what that says is the people need to know what's going on in other areas, and when they're working within their own areas, they need to think about what they're doing in terms of how it will feed into this overall development of an actual functioning system. Particularly when we think about communication and control, there's really an ultimate issue at this point that is out there. We don't as yet have the answer to it, but I refer to it really as the Grand Canyon problem. So this is a person standing at a precipice overlooking the Grand Canyon. Now this person could have come up to this with a BCI operated wheelchair, or a BCI operated exoskeleton, or a BCI operated neuroprosthesis. But at this point, and I think for at least the medium term foreseeable future, no one without a death wish is going to use a BCI to stand here, to walk up to this precipice and stand there. Because at this point, they're nowhere near reliable enough to be used for such a function. The problem of reliability is a very fundamental problem that applies essentially to all BCIs at this point, whether they're invasive or non-invasive. And it's something that I don't believe we really understand all the reasons for this problem, or everything that's going to be necessary to resolve these problems. We're clearly making some progress in that regard. I think Lee Miller tomorrow, when he talks about BCIs for control, will talk about some of the ways in which we're making progress at beginning to address this problem. But the Grand Canyon problem is sort of the ultimate problem for control BCIs. And until that's solved, brain-computer interfaces will not really have arrived as a control modality. So finally, in terms of basic science BCIs, I think obviously they don't face all the problems that other kinds of BCIs face. They don't necessarily involve these particular issues. Their issue, I think their fundamental issue, is to look at phenomena that relate to actual nervous system function. The nervous system is a very neat device. It's a very neat network of interacting elements. It presumably can be used to do many different things. Many different kinds of paradigms could be set up. But in using BCIs to look at basic science, I think it's important to consider that you want to set up a paradigm that has relation to how the nervous system functions in real life, because that's what you're interested in learning about. So there's also, in that case, there's going to be importance in looking at what actually happens in real life, here really in the clinical sciences. How does the nervous system operate in real life? How does the experiment that's being set up relate to what's going on in real life? So this, again, the multidisciplinary issue is the main issue I want to stress in terms of setting up this meeting. And all I'd like to say really at the end is that people should think about that. And this meeting, that's really the origin of how the meeting was established, to encourage interactions among multiple disciplines, to bring people from multiple disciplines together so that they recognize each other, they begin to understand each other, and they interact. So at the end, I would just like to say that you should go forth and interact over the next 5 days and hopefully move forward the field of brain-computer interface research. Thank you.